Hello everyone, welcome back to the course on materials informatics. In this lecture we will be sort of furthering our discussion on classical models. So just as a recap of what we done in the last what we did in the last lecture. So we looked at both linear and polynomial regression. We looked at the definitions of bias and weights that contribute to a machine learning model, and these bias and weights sort of come throughout all the other machine learning models as well. We looked at one specific algorithm, which is gradient descent, which is used for fitting machine learning models. We also looked at a few hyperparameters such as learning rate, your tolerance limit or epochs, and also batch size that is involved during your training. We looked at a very important trade off, which is bias variance. So the more the bias in a model, the less the variance. So the more regularized your model, the less tendency it has to overfit. And we also looked at using learning curves to understand this bias variance trade off. And then we broadly looked at the idea of regularization and how that can be done by adding a penalty term using ridge, lasso or elastic net regressions. These are commonly employed alongside your linear or polynomial regression models. We also looked at early stopping as a way to regularize our models, and early stopping is a very powerful tool which is often used in more complex models. So in this lecture we will look at a few other classical models that are commonly used for machine learning purposes, and as mentioned before, all the schematics that I am going to be using, unless otherwise specified, are from this book by Aurélien Geron. Okay. So let us look at a new model which is referred to as logistic regression. Although the name states that it's a regression, it's actually a classification model, right. So what does this logistic regression do? So it works pretty much like a linear regression, but instead of outputting a continuous value, a floating point number, it outputs a probability basically. So in other words, it outputs a logistic for a given set of features, right. So mathematically, if you look at a linear regression model, right, so you will just have h theta of x as x transpose times theta. So x transpose is your set of features, theta is your set of weights and biases, right. So just this is your linear regression model, but in logistic regression, whatever is the output of this x transpose times your theta, you pass it through some kind of a logistic function or an activation function here, which is represented by sigma, right, and the output of sigma is what is the output of your logistic regression model, or your p, your probability here, right. So sigma can take various forms. One of the classic sigma functions is your 1 over 1 plus exponential function here. So the t parameter here is basically your x transpose times theta here, right. So both are the same parameters. So if you were to plot the variation of this sigma function as a function of t itself, as a function of its parameter, you see that it sort of is very close to 0 at low values of t, and very close to 1 at high values of t, and sort of goes through a transition, right, or some kind of an activation here, right. So if your output, so if your sigma of t is a value if your sigma of t has a value of less than 0.5, then your logistic regression model classifies that output to be false. If it has a value greater than 0.5, then it classifies that output to be true. So 0.5 is almost always taken as your decision threshold here, right. So of course here we are dealing with sort of standardized and normalized features here, but we can always define some kind of a threshold value below which your logistic regression will output false, and above which it will output true values here, right. So that is in short how logistic regression works. And as with linear regression, right, so where we defined a few metrics, performance metrics to identify or quantify the performance of the model, such as root mean squared error or mean absolute error. In logistic regression also we have to introduce some parameters. So we introduce a new function, what we call an objective function called the cost function here. Right. So the cost function for any set of weights and biases is defined as negative log of p, right. So p is your output value here, right. So it either has a value of 0 or 1, So it's negative log of p for the target values which are 1 and negative log of 1 minus p for target values which are actually 0. So y is your target and p is your predicted value, your probability, right. So what does this cost function basically translate to? So the cost function acquires very large values if your p is different from your target value, right. So if your p were to be 1 here, which is the same as your target, then you have negative log of 1 which is basically 0, right. So your cost function is 0. But if your p were to be different, so let us say your p is actually 0, so it outputs a wrong value compared to your target value, then log 0 is actually negative infinity and you have a negative sign here, so you have infinity value coming into your cost function here. So the cost function sort of blows up if your prediction is wrong compared to the target, and if the prediction is correct compared to the target, then it is 0, right. Same thing can be sort of applied for your target values of 0 here, right. So keep in mind that this sort of works when we have a classification model, a binary classification model. Okay, so what we then do is take this cost function and define some kind of an objective function so that we get a smooth convex behavior and we can actually use gradient descent, right, to fit the model. So the way we define this objective function, this j of theta, so j is our objective function, theta is a set of weights and biases that influence the objective function, right. So m is the number of training data points that we have. So we sort of normalized it with respect to the total number of training data points. So we basically define this as negative summation of y times log p plus 1 minus y times log of 1 minus p, right. So whenever and y is defined for each data point or each instance here. So y is the actual value and p is the predicted value, right. So this sort of builds on the cost function here. So if y were to be 1 and the log of p is 1, then your objective function is sort of goes to 0, but if y and p take opposite values, then your objective function sort of blows up to infinity, right. And if you look at this functional form, right, so it sort of looks like x log x plus 1 minus x log x, log of 1 minus x. So this objective function is very similar to your ideal solution entropy. So if you are familiar with simple materials thermodynamics, ideal solution is one kind of solution model that we often use to describe systems, and the entropy term sort of looks like x times log x plus 1 minus x times log of 1 minus x, right. So the nice thing about this objective function, which is derived from this cost function here, is that it is a very nice convex function. So just like your root mean square error, for example, which is a very nice convex function for linear regression, this is a very nice convex function, and hence you can simply use gradient descent as your optimization algorithm, right. So how do you implement logistic regression? So you can use so you can import logistic regression from scikit-learn.linear model package, right, a linear model module. And then you define your logistic regression instance and then simply use the fit function, right. And just like your linear regression, your logistic regression can also be regularized by adding a penalty term to the set of features that you have. The only difference is that instead of alpha, which is often used as a penalty term in linear regression with ridge or lasso, we use a hyperparameter called c. So c is you can sort of roughly consider c to be 1 over alpha, right. So in linear regression, higher values of alpha implied more regularization of your model. Here higher values of c imply that your model is less regularized, right. So c is inversely proportional to that of alpha. So that is the only difference. So we can add this penalty term in the form of c and add regularization on top of our logistic regression model, right. Okay, so now that we have understood a little bit of how logistic regression works, we can now extend logistic regression to perform multi-class classification, right. So recollect that logistic regression is a classification model, and as used it can only do a binary classification. So you can either output a true or false, so 0 or 1, right. So in multi-class classification you can output one of several values for any given data point. So you can output either 0, 1, 2, 3, 4 and so on. So if you recollect our MNIST exercise, we had 10 possible outputs from 0 all the way to 9. So if you were to predict an incoming digit, an incoming figure to fall under one of the 10 different labels that it can take, then that is referred to as multi-class classification, right. So you basically classify your data point into one of several possible classes, right. So extending logistic regression to perform multi-class classification is basically what is referred to as softmax regression. So once again, although the name is softmax regression, it is actually a classification model. So how does softmax work? So there is a sort of slight modification in how the probability or the logistic is defined. So first you define an SK function here, so which is nothing but your transpose of your features times your set of weights and biases, but you define this function for a given class K, right. So if you take the MNIST database, so you would define your S function here, right, as a function of your features for predicting or outputting a value of 0, outputting a value of 1, outputting a value of 2 and so on, right. So for each possible value of K you define this SK function here, and then now you define your probability as basically the exponential of this SK output here divided by the summation of all the exponents over all the possible values of K, right. So if you are familiar once again with a little bit of statistical mechanics, right, so this sort of looks like some kind of a Boltzmann distribution, right, but anyways we will get back to statistical mechanics a little later in the course, but basically we define some kind of a normalized version of an exponent of your SK function as our probability here, right, as our logistic here. And the output class itself, right. So what the model eventually ends up predicting or classifying is it basically predicts the K value that maximizes your logistic here, right. So let us say you have 10 different outputs, right. So for 0, 1, 2, 3 and so on, let us say the maximum probability you get is for K equals 4, right, then the output class would be 4, right. So the output class is basically whichever K, whichever label or class maximizes your probability here, right. So this is how softmax regression works, and the loss function or the objective function of softmax regression is very similar to the entropy like objective function that we saw in logistic regression, but we generalize it to basically account for a cross entropy term, right. So we basically define an objective function here J of theta here, theta is a set of features. We basically define a summation over both all the features and for different classes that M is the set of data points here, so we define it for all set of data points and for all the possible classes that each data point can take, right, and we basically define the objective function as the target value times the log of the probability value, right. So once again if the probability is very similar to the target, then this goes to 0, if the probability is very different, then this value can blow up, right. So this is an example of a cross entropy term. So if you were to look at this in a simple mathematical fashion, this is just a summation of x times log x, right. So that is why it is called as cross entropy. So how can we implement how can we regularize our softmax regression? We can regularize it just like we regularized our logistic regression model here using the hyperparameter C, right. So just like logistic regression uses this hyperparameter C, which is inversely proportional to alpha that we used in linear regression, we can use the same hyperparameter to regularize our softmax regression here. And how do we implement softmax regression? We can use the same logistic regression instance, just that we have to define this multi-class attribute here as multinomial, right. So once we define this, we can generate a softmax regression model. Okay. So now that we have understood a little bit of logistic and softmax regression, let us now go to a slightly more complicated model, which is K nearest neighbor, or popularly referred to as KNN, right. So how does this model work? So it basically calculates the similarity of any given data point with a set of nearest neighboring instances or nearest neighboring data points, where K represents the number of neighbors that you are actually considering, right. So if you are doing a 3 nearest neighbor model, then it will consider the 3 nearest neighbors and calculate the similarity of your new data point with respect to its 3 nearest neighboring instances, nearest neighboring data points. So in KNN models, you can either use them for classification tasks as well as regression tasks. In the case of classification, you basically take a majority vote. So let us say you have a new data point that the model is seeing. It calculates the similarity with respect to let us say 5 nearest neighbors, and then it takes a majority. So let us say 3 neighbors are of one type, 2 neighbors are of a different type, then it assigns the new data point to be of the first type, where the majority was 3, right. So it just calculates the majority among neighbor types and then assigns that as the label in case of classification tasks for any new instance. In the case of regression tasks, it basically takes an average of all the neighboring values. So if you take a new data point with 5 nearest neighbor regression, right, then it calculates the similarity metric with all the 5 nearest neighbor points and takes an average value, right, of all the 5 nearest neighbor data points. So that is what happens in regression tasks. The one thing that to note is that k nearest neighbor is an instance based learning model and it is not model based learning. So in the case of softmax regression, in the case of linear regression and polynomial regression, right, those are all model based learning. So you actually learn a set of weights and biases, right, for your given model, but here the model actually sort of memorizes all the instances that it has seen before, right, and only calculates similarities with respect to the instances that it already knows, right. So it does not try to come up with a more general sort of equation or mathematical function based learning of the underlying distribution of data points, right, that the model actually sees. So it simply memorizes all the instances, so that is why it is called an instance based learning model. And as with any instance based learning model, it is usually these k nearest neighbor models are very light for small data sets, so they are very quick to be implemented and used, but can very quickly become heavy for larger data sets, right. And since this is instance based learning, we need to ensure that all the features that we provide to the model are normalized. So in other words, we cannot give them unscaled or not normalized features, because that can really skew the way that the model actually memorizes all the instances. So there are also a few new hyperparameters that are introduced with respect to k nearest neighbors. The first one is actually k, right. So how many neighbors you actually consider with respect to calculating your similarity metrics. Especially in classification tasks, it is important to use an odd number of neighbors. So you can either use 3 neighbors, 5 neighbors or 7 neighbors, but not 4 or 6, because in classification tasks we rely on majority vote, kind of voting. So let us say you take 6 nearest neighbors and you use you calculate similarity metrics, and let us say you get an even number, right. So 3 are of one type, 3 are of another type, then the model cannot assign a label for the new data point, right. Whereas if it is 5 or 7, it can always break a vote, right. So you can always have a majority of one set of labels. So k is one important hyperparameter, and how do you actually calculate the similarities between different data points. So that is another hyperparameter. We typically use some kind of a distance metric, right. So distance metric in a functional space. So normally in Cartesian space it is very easy to understand the distance metric. In a functional space or in a parameter space, we can also define an equivalent distance metric. So the Euclidean is the sort of classical distance that we can define. So this is similar to how we define root mean squared errors or mean squared errors in general, right. Manhattan distance is similar to how we define mean absolute errors, right. So what kind of distance metrics we actually use to calculate the similarity between data points, that is another hyperparameter that we need to consider in k nearest neighbors. So let us just take a visual example of how k nearest neighbors works, right. So we have 2 classes of data points here. So one set of one class of data points which is sort of darker blue in color, another set of data points which is sort of lighter blue in color, and let us say this is a new data point that you are introducing to the model. So the first is the model will try to identify which points are its nearest neighbors, right. And then depending on the k metric, so let us say you have given 3 nearest neighbors as your criterion, so it will sort of shortlist 3 of the nearest neighbors, and here you see that 2 of the nearest neighbors are lighter blue and one is sort of darker blue in color. So it will label this data point, the new target data point, as light blue in color, right. So that is how k nearest neighbor works. So if it were regression, then it will take the average of these 3 data points. So whatever value this data point will have will be an average of this data point, and this data point, right. So how do you implement k nearest neighbors? So there is a module called neighbors module within scikit-learn. So from there you can either import k neighbors classifier or k neighbor regressor. So regressor is obviously for regression and classifier is for classification. So if you were to do a classification task, then you define the number of neighbors, right. So this is your k hyperparameter here. And the p hyperparameter basically indicates what kind of distance metric you are using. So p equals 2 indicates that you are using Euclidean, p equals 1 indicates that you will use Manhattan distances, right. And then you basically do a fit. So keep in mind that you should use normalized features here as much as possible, because k nearest neighbors models, since they are instance based learning models, they are very sensitive to feature normalization. So if you use unnormalized features, then the data points that are identified as nearest neighbors will be very different compared to, or can be very different compared to, if you use normalized features. So the advice is always to use normalized features in k nearest neighbor models. Okay. Let us now get to support vector machines, which is once again a different type of classical machine learning model. So we have looked at logistic regression, we have looked at softmax regression, and we looked at k nearest neighbors. So support vector machine is another different type of classical machine learning model. It can do both sort of linear or non-linear, so the model itself can be both linear or non-linear, and it can do both regression and classification tasks. And support vector machines are powerful models and sort of works well in small to medium sized data sets. For very large data sets, the model can take quite a bit of time to fit, and also for prediction tasks. No, so let us first take a case of simple linear classification, right. So here the support vector machine models scale of the order of m cross n. So m is the number of training instances or data points that you have for training the model, and n is the number of features that you have right in the model itself. So in the case of linear classification, we require data sets to be linearly separable, right. So in other words, the data sets should be able to be separated as cleanly as possible. So we do not have a large number of outliers in our data sets. And for illustration purposes, right, so to illustrate how support vector machines work, we are going to take this sample data set, which is the classification of setosa flowers. So setosa is a type of flower that is commonly available. Yeah, so the flower that we are going to classify is iris, not setosa. So we are going to take this iris flower classification task as an example. And there are 3 specific types of this flower, one is virginica, second is versicolor, and third is setosa. And the way the flower is classified is predominantly dependent on the features of the petal. So petal length and petal width, so how long each petal is and how wide each petal is, basically is used to commonly classify virginica, versicolor, and setosa. So those are the features. So petal length and petal width are the important features, and virginica, versicolor, and setosa are the labels that we should assign for our classification task. So to understand how support vector machines work, let us try to understand through this iris flower classification. Okay. So what does support vector machine do in terms of classification tasks? It basically tries to identify the largest street between data points, right. So let us say you have 2 sets of data points here, one corresponding to setosa and the other corresponding to versicolor, right. You can you can find a way to classify these 2 clusters of data points through multiple means, right. So one is you can arbitrarily try to draw a line here which basically represents your threshold. So anything to the right side of the line is versicolor, let us say, and anything to the left of the line is setosa. But this line is a very bad way to classify the data set itself, right. So this is a bad classifier, but we can also do two other good classifications, right. So we can draw this red line here, right, which completely classifies Setosa as below the red line and versicolor as above the red line, right, and we can also draw this purple line here, right, which once again can classify the blue and green dots completely separately, right. But these are single lines, so they do not actually separate the data points as efficiently as possible, right. So let us take this scenario, right. So where we identify this data point here and this data point here as our two main sort of our most outwardly lying data points among versicolor and Setosa clusters, right. So let us assign these two data points as our support vectors, right. So if we assign them, we can actually basically draw a very broad street, right, or a very broad window of petal length values and also petal width values where none of the data points are actually present, right. So in other words, we have drawn a street that has completely separated out our Setosa data points here and our versicolor data points here, right. So this is basically the objective of support vector machine. So it tries to separate the data into clusters as distinctly as possible. So basically it tries to draw streets or identify streets that can completely separate out your classes of data points, right. So the most outwardly lying data points are normally referred to as support vectors. So the objective of support vector machine is to identify these most outwardly lying data points of the set of data points that you have, right. So this sort of data set example is actually an example of a linearly separable data set. So where you can completely separate out all the Setosa data points with all the versicolor data points, right. And if we were to create a support vector machine classification that is devoid of any outliers, so you see that in this cluster of data points there are no green dots here, and this cluster of data points there are no blue dots here. So if this were the type of classification that we want to do, then it is referred to as a hard margin classification, right. So where there are no outliers on each of the data points or each of the clusters. But if there were outliers now, right, and if you want to create a hard margin classifier, we see that this is impossible now. So you will never be able to draw a street that completely separates out this green dot along with all the other green dots. So this is basically an outlier, right. So in such a case we can sort of reduce the constraints of our model to have or to consider some outliers. So we basically try to draw a street as wide as possible, but with the consideration of a few outliers. So with the fact that there can be a few outliers that can be present in both our versicolor as well as Setosa data points, and if we were to do this classification task, then it is referred to as a soft margin classification, right. So hard margin we do not allow any outliers to be present, in soft margin we do allow some outliers to be present, right. So support vector machine can do both hard margin classification as well as soft margin classification, and in both cases it will try to draw as wide a street as possible or identify as large a street as possible, okay. Just like k nearest neighbors, support vector machine can also be quite sensitive to feature scaling, right. So let us say you take a set of unscaled features here, right. So you have blue data points that are separated out here, and then sort of purple data points that are separated out here, but let us say using unscaled features you are able to draw a very narrow street here. But with feature scaling you could have a nicer separation of data points. So your purple could look like here and your blue could all be separated out here. Now you see that you can draw a much wider street, right, which is more resistant to the presence of outliers. So in general if you draw narrow streets, the street can actually change or fluctuate quite rapidly with outliers, but if you have a wider street then it is more resistant to outliers, right. So we want to draw as wide a street as possible in support vector machines, right. So in general if you use standardized features you will have a higher chance of being able to identify wider streets or larger streets, right. So in support vector machines always try to use standardized features as much as possible, just as with the case with k nearest neighbors where you use normalized features as much as possible. One important hyperparameter that is associated with support vector machines is the C hyperparameter. And this is basically a regularization hyperparameter similar to our logistic regression as well as softmax regression, right. So what C hyperparameter does is that it basically controls how many margin violations or how many outliers can your model actually resist. So if you have low values of C, your model basically is very highly regularized. So in other words, your streets are forced to be as wide as possible, and your model needs to basically take in a large number of outliers, right, because your model cannot overfit in some sense, right. So you have low variance and high regularization, but if you have larger values of C, then you can have high variance and low regularization. So your model will take in fewer outliers, or your model has a higher tendency to overfit, right. So basically think of C as your control of margin violations or as your control of regularization. So narrower streets, or the model is not regularized as well, wider streets the model is regularized more, but this can lead to more outliers, this can lead to fewer outliers, right. So this is a hyperparameter that we need to optimize for our given task. Okay, so how do we implement support vector machine? So there is a separate module called SVM module within the scikit-learn package from which we can import one of the support vector machine classes. So if you were to do a linear support vector classification, you can use linear SVC. When you initialize an instance of your linear SVC, you can then define your hyperparameter, which is the C hyperparameter here, and then you simply call this fit function here, right, which is the and keep in mind that when you call the fit function, you take in your scaled, so basically your standardized features along with the target values, right. So with this we will stop this lecture, but we are not done with discussing support vector machines completely. So in this lecture we discussed logistic regression, softmax regression, k nearest neighbors, and we started introducing support vector machines, and in the next lecture, which will be a continuation of this lecture, we will discuss little more on support vector machines, especially on their non-linear classification and regression tasks, and we will also introduce a different classical model, which is the decision tree model. So with this, thanks a lot for joining today's lecture. I will see you in the next one.